This is an introduction to small-step operational semantics, and before I continue, please make sure that you are aware of abstract syntax, that you know about basics of interpretation, and most importantly, that you already know what big step style of operational semantics is like. This is very much assumed in what follows. Any semantics definition, be it small step style or big step style, assigns meanings to language elements. As before, we use the BTL, basic tuple language, as the running example here. So we've got expression forms or constant forms, true, false, and zero, and we can build successor of a natural number with suc, the predecessor of a natural number with pred. We can test the natural number to be zero or not, and we have an if then else expression form. So here's the major difference between big step versus small step operational semantics. In big step style, we really relate program phrases, such as BTL's expressions, to results, such as values in the case of BTL. In small step style, it's all about just making progress with execution or evaluation. So we want to perform one step of computation. So this means in the case of BTL, we relate two expressions. One expression is given and the other expression corresponds to expression where one step of computation has been completed. So why should we bother? Well, it turns out big step style is very easy to understand because it corresponds closely to the intuitive style of writing recursive interpreters. However, there are some problems with language constructs where it's hard to impossible to actually assign a big step semantics to. So this is not proven here, but please see the book for some details. So overall, it's difficult to deal with interleaving parallelism in big step style. The same is true for exception, throwing and handling, or languages with goto. It's also generally true if you expose steps of computation, if you make them more observable, then certain activities in language implementation become easier. For example, debugging becomes easier because we can just observe all the intermediate steps very easily. And if we have more complicated model-driven engineering scenarios where multiple languages and their semantics need to be integrated, that's also easier when we have many steps exposed. So here we look at the big step versus the small step semantics for a few constructs, zero, suc, and pred for the BTL language. And as you can see, there is actually no rule for zero in the small step style. Well, that shouldn't be surprising because there's no step to be made for zero. Zero is already a result. It's already a value. Now, if you compare the rules for suc, they look very similar, except in this case, in the big step style, we assume that we reduce the argument, that we evaluate the argument e completely to a natural number. Whereas here, we just assume that we may perform one step of computation with e. And so, of course, we cannot assume that e is immediately in value form here. So we have the same sort of rule for suc, we also have it for pred. And we have separated out these two rules that deal with the different natural number forms. Okay. So now here are all the rules. On the left, there are the rules that we just have seen. On the right, there are the remaining rules. So it's important to realize that for every construct, suc, pred, is zero if, for every construct, we always have at least one rule that deals with making progress with some argument position. So, okay, suc and pred and it's zero, they only have one argument position. So obviously it's about simplifying the argument, and then when the argument has arrived in value form, then there might be additional rules. So for if, it's all about the condition position of the if. So this rule here, we try to simplify the condition position, and once the condition position is in value form, then we can select then or else branch. So in order to perform a complete evaluation or execution, in small step style, we need a derivation sequence. So we need to apply the relation maybe many times. So here we show how a complex term, pred, if, etc., is step by step simplified to 0. So of course, each of these steps involves let's say, small or simple derivation tree. Just in the same sense as in big step style, we had one, let's say, big derivation tree for the complete evaluation. So here's one derivation tree, namely the derivation tree for the first step, where we essentially end up simplifying the condition position of the if expression, right? And of course, it's a derivation tree very much in the same sense as in big step style. So we can also take the reflexive transitive closure of the small step relation. We refer to it as arrow star here. So the idea is that we try to apply the small step relation as many times as possible. So if it's no longer applicable, whatever phrase we get, then we call it a normal form, something that cannot be further simplified with the small step relation. And indeed, there are two kinds of normal forms, informally, let's say. So one we might call proper results. So these are things that we expect as the outcome of computation, like in the same sense as we get those results with a big step relation. But it might also happen that computation gets stuck, that we encounter terms to which no rule is applicable. So for example, pred true, there is no rule for pred if the argument of pred is a Boolean. So we can map small step operational semantics also to Haskell to get an interpreter directly, at least an interpreter for the stepwise computation. And that's pretty much the same scheme as for big step operational semantics. So we have like one equation per rule, and the conclusion contributes to the left-hand side pattern here and to the right-hand side of the equation. And the premises, if any, they might end up as pattern gods. Well, and in this case, since it's so common that we may encounter expressions to which no inference rule is applicable anymore because they are already in value form, in this case, it's really important that we wrap the result of the step function in a maybe, so that we make it properly observable that no step is possible anymore. Let's also look at the small step semantics of simple imperative programs. In this case, a judgment involves a store before the step, the statement with which to perform a step, the store after the step, and the statement after the step. So indeed, here we look at the semantics of assignment, and just like in big step style, we need to evaluate the expression of the right hand side. So in fact, we assume that only statement execution is in small step style here, and we keep expression evaluation in big step style. Okay, so other than that, what we do is we update the store in a position X to return V, and the remaining statement is the empty statement skip, because after an assignment, nothing is left to be done. By the way, we don't have any inference rule for skip, because there's, again, no step feasible for the empty statement. There are these two rules for sequential composition. So the first rule is about the case that the first operand of sequential composition is the empty statement, and if so, we just return the second operand of sequential composition as the remaining statement. Otherwise, we just try to make a step with the first operand, and we put back the resulting progressed first operand, we put it back into the sequential composition. There are two cases for ifs and else statements. Either we can evaluate the condition to true or to false, and depending on that, we either return the statement from the then branch or from the else branch as the statement to continue with. In the case of the while statement, while we essentially just form this complex if statement here, but we don't really perform any other step. So we say, okay, to make one step with a while statement, we form an if statement which evaluates the condition of the while loop, and if the condition holds, we sequentially compose the body of the while loop with the while loop itself. If the condition doesn't hold, we resort to the empty statement. Finally, here's also the small step semantics of simple functional programs. So the first rule for if expressions deals with the condition position of the if expression. So we try to simplify the condition and we put it back here. We reform the if expression. The second and the third rule assumes that we may have true or false, and then accordingly we resort to the expression from the then or the else branch. And the last two rules deal with the semantics of function application. So the first rule deals with evaluating actual arguments. So basically we pick the leftmost actual argument that is not yet a value, well, or for which we can at least make a step, and that certainly implies it's not a value. And the second rule assumes that all the actual arguments are in value form. And so what we do here is we look up again the function from the list of functions, and then we actually perform substitution. That is, we replace the formal argument names by the actual argument values within the expression e, which is the body of the function that goes by the name x. So that's also an interesting point here, that we do not form any environment or any context, but rather we use substitution to actually replace occurrences of variable names or argument names by the corresponding values. This is necessary because we are on small step style, so using an environment would not be straightforward here. Okay, that's it. There are Haskell and Prolog based small step style interpreters in the repository, and the book discusses operational semantics in much more detail, but it also discusses denotational semantics and eventually also lambda calculus. Thank you.